Hi everyone, welcome back. In this lecture we're going to get into articulation points and biconnected components. Now this will be an application of the depth first search spanning tree. So we're going to see how we can use that to design or develop other algorithms to answer questions about graphs. So let's get into what are articulation points. The idea behind articulation points and biconnected components is to get a feel for how robust your graph is in terms of its connectedness. So here I'm going to just draw an example of a graph. And I'm going to imagine that this graph represents a physical network. In other words, the nodes are going to be servers, and the edges connecting them will be basically wires connecting them. So we'll label them here. This will be server A, B, C, D, E, F, and G. So what we're doing is we're thinking, or let's say we imagine, the vertices are servers and the edges are cables. So the cables connecting the servers. Now, the question I'd like to know is, what happens if a server goes down? Are there going to be other servers that now cannot communicate with one another because they relied on the connection that went through that server that is now down? So for which servers in other words, which vertices will the server going down, or in other words, going offline, result in a disconnected network? So where is my network vulnerable? If a server goes down, which other servers will now no longer be able to communicate? And this is something that you could probably just eyeball. You look at the network and you say, oh, D is definitely a problem. Because if that server went down, then all the communication that's going into that server and then out of it, that'll all be lost. And so we get that this part of our network no longer has the ability to communicate with this part of our network. And so that's an issue. So this is a very vulnerable spot in our network. Can you see another one? Is there another vertex which is vulnerable? If that vertex as a server goes down, or if you want to think of it this way, if that vertex is removed from our graph, is the resulting graph disconnected? And this gives rise to what we call an articulation point. So that's our definition down below. So in a graph, a vertex V is an articulation point if removing that vertex increases the number of connected components. So in this example, our graph is already connected, so we're looking at those vertices which, when we remove them, disconnect the graph. But in general, an articulation point is a point that when you remove it, the number of components of your graph increase. So did you spot the other one in here? The other one is vertex B. If we remove vertex B, then what happens is vertex A is now no longer connected to the rest of the graph. And so removing B does disconnect our graph. So now with this new definition, articulation points, let's go ahead and write down what they are. We've already seen that D is one of those vertices, and so is B. Are there any other vertices in here? Well, we would just systematically go through and imagine, what if I removed it? What if I removed A? What happens? Nope, everything that's left is still connected. What if I removed C? No, everything left is still connected. What if I removed E? No, everything else is still connected, and so on. We could just systematically go through them. There are a couple of observations that we can make. So what are some observations? Well, a vertex of degree 1 is not an articulation point. So if we remove a vertex of degree 1, there was no risk at disconnecting the graph. And so that, for example, tells us that A is not an articulation point. Vertex A is not one. What else do we have? Well, a vertex of degree 2, which is on a cycle, is not an articulation point. And that's just because if I have a vertex of degree 2 and I remove it, if it's on a cycle, then there are other ways to get to those vertices that were on either side of it. You just go around the cycle the opposite way. So for example, G is a degree 2 vertex. But if I remove it, there's no problem because it lived on a cycle. So the vertex that was on one side of G and the vertex that was on the other side of the G, they're still connected to each other. Is there any other vertex of degree 2 that lives on a cycle? Oh, yep, C is. So we immediately see from this that C and G are not, and I'll underline the word not again, they're not articulation points. And so we've got some quick ways to say, yep, that's not an articulation point, it's a degree 1 vertex. These aren't articulation points, they're degree 2 vertices that live on cycles. What about the other vertices? Well, then you can go ahead and systematically check them. Our goal today is to actually come up with an algorithm which will produce the articulation points, and an algorithm that's much more effective than just systematically going through and imagine removing them. But we'll get to that later on. For right now, just imagining in our minds, if I remove it, does it disconnect the graph? Nope, it's still connected, therefore it's not an articulation point. So that brings us to our first lemma. This is a characterization of an articulation point. So a vertex V is an articulation point if and only if, so this is a characterization, if and only if there are distinct vertices x and y such that x and y are not equal to V, and every path between x and y has to include V. So this says V is an articulation point if the only way to get from some vertex x to a vertex y is always through the vertex V, then V must be an articulation point. The proof of this is left as an exercise, and it really just follows from the definition. So this will be an opportunity to just look at how to take a definition and use it to prove a result. Instead, what I'm going to do with this is I'm going to use it to find the articulation points of our previous example. So let's go back to our previous example. Let's copy this, and we'll paste it here. And now what we're going to do is we're going to use this result to find the articulation points. So how are we going to use this result? Well, consider vertex A and G. So we'll just draw our attention to those. We've got these two vertices, A and G. And now just think about all the paths that go from A to G. So no matter what path you take, what do they all have in common? Well, if you notice, they all have to pass through vertex D, and they all have to pass through vertex B. So if we consider vertex A and G, every AG path passes through, or includes, passes through vertices B and D. So therefore, B and D are articulation points. They're APs. So that's another way we could see that B and D are articulation points, is we can, instead of just imagining them being removed and seeing if it disconnects it, we can look at two vertices on the graph and all the paths that go between them. If they all have to use B and they all have to use D, then B and D are articulation points. The other concept I want to introduce is a notion of being biconnected. So what does it mean for a graph to be biconnected? This is more robust than just being connected. A graph is called biconnected if it is connected and has no articulation points. So that means it's connected, but it's robustly connected. If I remove any vertex from the graph, it remains connected. So that's what it means to be biconnected. It's connected, and it's so robustly connected that removing any vertex will not destroy the connectedness of the underlying graph. A biconnected component of a graph is a maximal biconnected subgraph of our graph G. So that's what we call a biconnected component. We call those BCs for short. So let's have a look at what are the BCs of this graph. So these are the subgraphs that are biconnected, and they are the maximal subgraphs that are biconnected. So let's think about A, vertex A. Is vertex A itself a biconnected subgraph? Absolutely. If you remove the vertex, you don't get any more components. But we could extend that and also include vertex B. That is also a biconnected subgraph, and it's bigger than the one that was just A alone. But I can't extend this anymore, because as soon as I add another vertex or even another couple of vertices, the problem is I end up with this being a articulation point, and its removal is going to separate this piece from this piece. So that is no longer biconnected. So that means that this is a maximal biconnected subgraph. And we can keep going. And what's another maximal biconnected subgraph? Well, I can look at this subgraph, which is just the triangle BCD, and that is biconnected, and it's maximal. I can't add any more vertices from the original graph to this one without introducing articulation points. What else do we have? Well, we can go D, E, F, and G. That's also a biconnected graph, and it's maximal as a subgraph of our original graph, which we didn't name, but I'll call it G. So those are the biconnected components of G. We've managed to split G up into a bunch of subgraphs, each of which is biconnected and are the biggest possible at being biconnected. So in contrast, we'll give an example of a subgraph that is not a biconnected component. So let's consider E, F, and G. This is a biconnected subgraph, but it's not maximal. I can extend it to a larger subgraph, which is still biconnected. Namely, I could extend it like this. That would still be biconnected. So it's not maximal, and so that means, therefore, it is not a biconnected component. And so the key thing here is I'm emphasizing maximal. A biconnected component is a biconnected subgraph, which is also as big as possible. So it's maximal. And so our goal is going to be coming up with a method for finding the articulation points and for finding the biconnected components of a graph. Before we do that, though, let's make a connection with Hamiltonian cycles. So in this lemma, we have G as a graph, and we have that if G has a Hamiltonian cycle, then it must have no articulation points. So this is a necessary condition of having a Hamiltonian cycle. So we're going to add this to our list of all the necessary conditions that we've had in the past. Now we've got another one. So how do we prove this? So we're going to let G be a graph with a Hamiltonian cycle. Now we just need to show that it doesn't contain any articulation points. Well, since it's a graph with a Hamiltonian cycle, then there is a spanning subgraph. So spanning includes all the vertices, subgraph, which is a cycle. So that's what it means to be a Hamiltonian cycle. It's a cycle that contains all the vertices. So it's a spanning subgraph, which is a cycle. So that means I can draw it out. So we have, let's say, vertex 1, vertex 2, vertex 3, and so on, all the way around up to vertex n. And those are all the vertices of our graph G, and they live on this cycle. And now what we can see is that this is a substructure of our graph. So this lives inside our graph G. And what we see is that removing any vertex, it's not going to disconnect the graph because there's a way to connect all the other vertices. So if any vertex is removed, the graph is still connected by, now it's connected robustly in the sense that it's connected by a Hamiltonian path. There's a path that connects the underlying vertices that are left. So if I remove any vertex, the remaining vertices still have a Hamiltonian path that connect them all. And so therefore, there are no articulation points. And so there we've got a necessary condition. If we have a Hamiltonian cycle, then there are no articulation points. The exercise that I want you to ponder is to find a biconnected graph which does not have a Hamiltonian cycle. So find a graph that's biconnected, so it has no articulation points, but does not have a Hamiltonian cycle. In other words, what are we asking here? We're asking to show that the converse of this lemma is false. So show the converse of lemma 7.3.2 is false. Again, why are we asking this? Well, again, this is a question about Hamiltonian cycles, and we've already spent a little bit of time talking about how we don't have a criteria for Hamiltonian cycles. We have necessary conditions, we have sufficient conditions, but we don't have a necessary and sufficient condition. So here's a necessary condition. If it's got a Hamiltonian cycle, then it must have no APs. We want to show that that is not a sufficient condition. Having no APs is not enough to guarantee there's a Hamiltonian cycle. And so that's what we're asking here. So to show that that's not enough to guarantee it, find a graph with no APs and show that it does not have a Hamiltonian cycle. So I'll leave you to ponder that one. Now we are interested in algorithms for finding articulation points. The first algorithm I'm laying out here is just it's in some sense the obvious one, the one we applied almost immediately as soon as we knew what an articulation point was. An articulation point is a point that when you remove it, the graph becomes disconnected. So that's our first algorithm. We take as an input a graph, and we return as an output a set of vertices, which are the articulation points. How do we find them? Well, for each vertex, do the following. Remove it and check to see if it disconnects G. If it does, it's an articulation point. Add it to the set of articulation points. If it doesn't, then just loop around and check the next vertex. And so that's sort of our obvious one. Just go one by one. Remove it. Does it disconnect? Yes. Articulation point. Nope. Not an articulation point. And then keep going. Now this seems to be a fairly straightforward algorithm in the sense that it was pretty much the one we came up with almost initially. And it does work extremely well on small graphs. The problem is, on larger graphs, it becomes a little bit computationally intensive. So for example, consider a cycle of length n. So it would look like this. 1, 2, 3, and so on all the way around up to a vertex n, and we'll close it off. And now let's imagine going through the algorithm to find the articulation points of this graph. So what we would end up doing is we would be looping over all the vertices. So we'd start at vertex 1, we'd remove it, then we'd check the resulting subgraph for being connected or not. Then we'd remove 2, check the resulting subgraph if it's connected or not, and so on. And so what do we notice here? Well, we are looping over the vertex set. So that's going to take like n operations. So I'll use big O notation here, but this is really just saying it's the number of operations I'm going to have to do is on the order of n, because there's the loop is going to have to run n times. Now within that loop, I'm going to remove the vertex and check the underlying graph to see if it's connected. So what does it cost to check whether a graph is connected or not? Well, to check if G take away V is connected, we can use the depth first search algorithm. So we use DFS. Because if DFS returns a tree which contains all the vertices of G take away V, then we know it's connected. And what does it cost to do a DFS? Well, that's again of order n, just the number of vertices. So we can check if it's connected by using the DFS, and this also costs on order of n operations. And therefore, we're going to loop n times, and on each check, we use a algorithm DFS of order n, and so it's of order n squared to do this full algorithm. So the cost of the algorithm is order n squared. And so the big question is, can we do better? Can we do better? It would be great if we could come up with an algorithm that runs in linear time rather than quadratic time. Nice improvements on speed if we could do that. And in fact, we can. And that's our second algorithm for finding articulation points. And that's what we're going to finish up with. I'm going to describe what the algorithm is through an example, and then we'll do a following example of running the algorithm start to finish. And our goal is to produce the articulation points and the biconnected components of a graph using this algorithm. So let's start with our graph that we had from before. And we'll follow the instructions. So this is our graph G. We are going to construct a DFS spanning tree T for our graph, and then number the edges in the order we visit them. Now in order to do that, we need to start somewhere, so we have to have a root. So let's root it at, and we can really root it anywhere, so I'm just going to root it at D. So we root it at D, and we will assume alphabetical ordering. Now what does that mean? Of course I know you know what alphabetical means, but what do I mean by assume alphabetical ordering? Well, remember, during the DFS we have to take an ordering of our vertices in, because I need to know when I'm at a particular vertex, I have to then take the smallest neighbor to continue my path along. And so what do we mean by smallest neighbor? Well, we're going to use alphabetical ordering to determine what we mean by smallest. And so here is the result of our algorithm. We're going to start rooted at D, and then what are we going to do? So the DFS says find the smallest neighbor of D, and the neighbors are B, C, E, and F. B is the smallest one, so I'm going to go from D out to B, and that's going to be the first edge I introduce. So we'll go D out to B, and that's edge number 1. And then what do? Well, now starting at B, we now find the smallest neighbor, and its neighbors are A and C, or the smallest unvisited vertex. So its neighbors are A and C that haven't been visited. A is the smallest, so that's our edge number 2 in our DFS. And so we get A there. And then we backtrack, because now A has no neighbor. So we backtrack back up to B, and then is there a smallest unvisited neighbor? Yep, there is. There's C, and so we add that edge. That'll be edge number 3. So it looks like this. And C has no unvisited neighbors, so we back up to B. B has no unvisited neighbors, then we back up to D. And now D has unvisited neighbors, E and F. The smallest one is E, so that will be our edge number 4. So we go out here to vertex E. E has 2 neighbors, F and G, both unvisited. F is the smaller of the two, so that's edge number 5. And I haven't been labeling them here, so I'll label them 2, 3, 4. And so E goes out to F. And that's edge number 5. And then from F, we have an unvisited neighbor, that's G. And that's edge number 6. And so we're going out to G. And there's edge number 6. And so now we found our DFS spanning tree. So that's the first step. Construct the DFS spanning tree and number the edges in the order that you visit them. Now before I get to step 2, I just want to do a bit of exploring. You know, what benefit do I get by doing the DFS spanning tree? Well, the benefit is as follows. There are 3 edges that are in our original graph that aren't in our spanning tree. Let me just highlight them. These are these 3 red edges. All edges not in T are what we call back edges. What does that mean? Well, they connect ancestors. Let's see that in our picture. So we have edge CD. So C's down here and it's connecting to D. So it's going, we like to think of it, it's going back up the tree. What about DF? So DF, so that goes from F all the way back up to D. So there's a back edge going back up the tree. And what about EG? That's another edge going back up the tree. And the thing to notice is the endpoints of all these edges are ancestors. So starting at C, D is an ancestor of C. We're starting at F, D is an ancestor of F. We're starting at G, E is an ancestor of G. So it connects ancestors. And that is a consequence of the depth first search spanning tree. This is a really important consequence of the depth first search spanning tree. We're not going to get, for example, an edge that goes like this from G to C. That just won't appear. The reason why is because imagine when we're doing the depth first search spanning tree, I'm here at C and then I'm trying to push forward. If there was an edge that connected C and G, then that means G wouldn't appear over here, G would appear over here. And so as a consequence of the depth first search spanning tree, any edges that aren't used in the spanning tree that are in the original graph are basically back edges in the DFS. So if I add them to the DFS, the depth first search spanning tree, they become back edges. So this is a nice picture to have of our original graph, and I'll refer to it as the tree plus the set of back edges. And so that's our full graph there redrawn. So this is our full G. We can even write it like this. T plus back edges, that's our full graph G. So we've just redrawn our full graph G. So that's got an underlying depth first search tree structure with these back edges. And now what can we do? Well, we can ask the question, where are the articulation points? Looking at this diagram now, can we see the articulation points? Well, there's a couple of observations. One is any leaf. So again, I'm looking at the tree structure, so you can ignore the red edges. Just focus on the tree structure. In fact, what I usually do is I dot these red edges in because I don't want them to confuse me as to, hey, this is supposed to be a tree. But I do want them in the background because I want to know that they're there in the original graph. So I usually dot them in. So we've got a leaf here, a leaf here, and a leaf here. And we know that those leaves in the tree cannot be articulation points, because if I remove them, then the rest of the tree still stays and therefore is connected. So what we have is that a leaf in T is not an articulation point. And so we can immediately see that that rules out A, C, and G. They're not articulation points. We also get that the root is an articulation point if it has two or more children. So if it has two or more children, and that's because if I was to get rid of it, then the subtree with one child would be disconnected from the subtree for another child. And so if it has two or more children, then the root would be an articulation point. And in this case, D does have two children. So D is an articulation point. Okay, so that's one thing we can observe from that. Now what else? Well, what we've done so far is we've dealt with the leaves, we've dealt with the root, and now what about all the things in between? How can we decide if those are articulation points or not? Well, let's think about this. Before I write it down, let's think about it. Could B be an articulation point? And I want to get that information from this tree diagram. So could B be an articulation point? Well, if I imagine removing it, what happens? Well, this vertex would fall away. The C, however, would not, because it has this lifeline connecting it back up to a higher vertex. So I think of these back edges as like lifelines connecting it to vertices higher up the tree. So is B an articulation point? Yes, it is, only because A would fall away. C is still saved. Is E an articulation point? Well, if I cut E away, then it's got a child that still has a lifeline back up higher in the tree. And so E won't be an articulation point because this subtree is still saved. It's still connected to the rest of the graph. And so the idea is we are interested in knowing if there is a descendant that's connected by a back edge up to a higher ancestor. And if there is, then it's not an articulation point. If there isn't, then it is an articulation point. So what this means is other vertices V in T are articulation points if there is a child, let's call it C of V, such that the descendant subtree rooted at C, let's call that TC, has no back edges. So I'll put that in red just so we can see that we're using those back edges, those dotted lines in our diagram. Has no back edges going around V to an ancestor of V. So with that, what do we get? You know, which ones are articulation points and which ones are not of these three that are remaining? So the ones that are articulation points are the ones where there is a child of it for which the subtree rooted at that child has no back edges, leaving it wrapping around B and connecting to a higher ancestor. So there's one. There's a child, A, of B, for which there's no back edge connecting it higher up. So I know that B is an AP. What about E? Is E an AP? So I look at the subtree of the child of E, and there is a back edge that's connecting it to a higher ancestor. So if I remove E, there's still this back edge that keeps it connected. So E is not an articulation point. How about F? Well, for F, I look at its child, consider its subtree. Is there a back edge that connects something in that subtree to an ancestor higher up from F? And yes, there is. So there's our lifeline back up. And so F is not an articulation point. So we get two articulation points in this case. We get D and we get B. And so that's basically our algorithm. The first step was to do the DFS and the numbering of the edges. This next little bit, we still have to turn that into an algorithm. So this is step 2 of the algorithm. And we'll see how we can actually describe how to do this systematically. And so that's here, step 2. So what step 2 says is find a preorder traversal of our depth first search tree, and then do some processing of the vertices. If a vertex has a back edge down to some descendant, number all the edges on the walk with that edge number that started the path going down. And so let's see how we can do this. I'm going to copy and paste our previous work because this is what we're going to be building off of. So we'll copy this and we'll paste this here. So what it says is go ahead and find a preorder traversal. So what's our preorder traversal? So just a quick reminder that we can get the preorder quickly by sort of traveling around the tree like this and just listing our vertices. It's not, I mean, once you've done the preorder a number of times, you realize you don't really have to write it down. It's just a natural way to walk through the vertices of a tree. But the preorder traversal would be D, B, A, C, E, F, G. And then it says now start processing these vertices in this way. Start at the first one. If that vertex has a back edge from that vertex down to some vertex U, then do something. So I'm starting at D. Does it have a back edge going down the tree? Yes, it does. It's got a back edge going down to C. Okay, so then it says, look at the walk that goes in this way. It goes down the tree, and then last thing it does is come up along that back edge. So notice back edge is EN, and that's the last one here in our walk. So this is now walk down the tree and come back along that back edge. The number that's on the first edge of that walk, which is number 1 in this case, use that to update all the other numbers along that walk. So 1 is our first edge number. So that means this one is going to switch from a 3 to a 1. And our back edge is also get the number 1. And that's it. We then, I was going to move this along, but we got to pause for a second. Have we dealt with all the back edges? And the idea is, no, we haven't. There's still another back edge. So I look at this other back edge that's coming down. And we do the same thing. So we look at the walk that goes down to that vertex, comes along the back edge. That starts with a edge label of 4. So I just update all the edges with that label of 4. So this one becomes a 4 now, and that back edge becomes a 4. Now I've processed all the back edges coming out of D, and so then we move it along. Now we go to B. B has no back edges coming down the tree, so we move it along. How about A? A has no back edges coming down the tree, so we move along. How about C? C has no back edges coming down the tree, and I want to emphasize there that it's down. You might look and say, well, there is a back edge coming from C. Yeah, but it's going up the tree, and we've already dealt with that one because we dealt with it as it came down from the ancestor up above. So the key word is down there. So C has nothing coming down from it. No back edges coming down from it. How about E? E has a back edge coming down from it, and it goes to G. So I look at the walk that goes down the tree and comes back up along that back edge, and I just update all the edges with the appropriate number. What number? Well, the number on that first edge of that walk is 4. So all of the other ones get that number 4. So that's 4 and 4. And then we move along. F has no back edges going down, G has no back edges going down, and so we're done. We've processed all our vertices in that preorder traversal, and now we've just got a bunch of labels on our edges. What are the articulation points? Well, if I look at my graph, the articulation points, we already know this from before. B is an articulation point. But notice that B has some edges coming in with 1s, but it also has an edge with a different label, 2. And that turns out to be the identifier of articulation points. What are the articulation points? The APs are the vertices incident with edges with different labels. So if I look through my graph, D is a vertex that's incident with edges that have different labels. There's a 1 and a 4 on edges going into D. B is a vertex because there's an edge of label 1 and an edge of label 2. A is not, C is not. The only edges coming into A are all labeled the same. The only ones for C are labeled the same. How about E? E only has edges labeled 4 going into it. F has only edges labeled 4 going into it. G has edges only labeled 4 going into it. And so therefore, the APs are B and D. How about the biconnected components? What are those? Well, we can draw them here, the BCs. What are they? Well, we've already identified what our biconnected components are right at the beginning of this lecture, but now we're trying to see how this algorithm will be able to select those things off for us. And if we look at what the biconnected components are, we know that there was this one. So when I draw the biconnected components, the way I like to do this is I like to use information from this graph to tell me which vertices are in each component. And then I like to try to redraw this graph decoupled into the components. So I know one biconnected component is the AB, and that had an edge label of 2 here. Now I'm going to look at all of the edges that have the label 1 on them. All the edges with label 1 makes up this triangle. It's the DBC triangle. That's this triangle here, and we know that that's another biconnected component. So we've got the BCD biconnected component, and that just happens to have, I'll only put a 1 in the middle, that's just all of the edges with vertex label 1. Now if I continue looking this way, I see all other edges have 4 labels on them. So if I keep those all together, then what I get is I get the other biconnected component, which is D, E, F, and G, and that's the one that has 4s everywhere. And so that's how we can select our biconnected components. We just look at our DFS tree that had the updated values after we did the preorder traversal, and we just keep together all of the edges along with the vertices that have that same number. So what are the biconnected components? The BCs are the maximal subgraphs of T plus the back edges with equal edge labels. So by that I just mean look at your T with back edges and pick off the maximal subgraph that contains all the edge labels of 1s. So that's that one. Then pick off your subgraph that has all edge labels of 4, the maximal one, so the one that contains all edges with labels 4. Don't leave any of them out. That's what I mean by maximal here. Take them all. And then the ones with edge label 2. and those give you your Biconnected components. And so there's our algorithm in its full detail, start to finish, of how to get your articulation points and your Biconnected components. Why is this better than the first algorithm, which was just select a vertex, remove it, checked if it's connected? The first algorithm had a running time that was on order of n squared, where n was the number of vertices. This one, if you implement it carefully, will have a running time on the order of the size of the vertex set, so n, plus the size of the edge set. And so this one has the potential of running faster than the first algorithm. It does require us to do a DFS. The other one required us to do the DFS to check connectivity every time we removed a vertex. This only requires us to do one DFS and then a preorder traversal. And when we do the DFS, that's on the order of n, so the number of vertices, and the number of steps in doing a preorder traversal, again, is on the order of n. And so that's basically our algorithm. We implemented also at the same time as describing it. So what I want to do is just finish with one example where we run that algorithm start to finish. All right, so thanks very much for watching, and we'll see you again next time.